Hi everybody. Today the video purpose is to look at bond formation and electronegativity to determine how those electronegativity differences tell us if a bond's polar, nonpolar, or ionic, and also to take a look at what then makes a molecule polar. This is a really important topic because it helps us to understand how molecules interact with one another and just the different properties that we see from them. It helps us to use those properties in different applications. Like if you're thinking about, soap, why does soap work, and other industrial applications, dyeing clothes, all of these kind of lead into those properties. So understanding the molecule shape and its polarity and how it interacts with other molecules is a very important thing to understand. So what we'll look at today is bond formation and electronegativity. So electronegativity we defined before looking at the periodic table, and we said, well, atoms are more electronegative, meaning that they attract electrons within a covalent bond, and the atoms that are more electronegative are to the top and to the right in the periodic table. So fluorine will be the most electronegative element on the periodic table. Whenever an element is attracting electrons in a bond, it causes an unequal distribution of electrons, and we call that polarity. So this is due to electronegativity differences. So this is what it's showing here. It creates something called a dipole moment, meaning that there's more electrons around, like in this example it would be oxygen versus the hydrogen. And what happens is that we see this is representing a partial negative charge and a partial positive charge. So in this case, oxygen has more attraction for the electrons, and so it's partially negative, and then hydrogen is partially positive. When we look at electronegativity and use it to determine bond polarity, it tells us is a bond covalent, polar covalent, or ionic. And what we really see with this is that there's really a range of kind of bonds, and we define them as ionic and covalent, but really there's probably more of a range that a bond has more ionic character or more covalent character. So if you have a 0 electronegativity difference, then we call this bond a nonpolar covalent because the electrons are going to be shared equally between the two atoms. When we look at an intermediate, and we'll define this in the next slide, we call it a polar covalent, meaning that the electrons are still being shared between both elements, but they are not being evenly shared. And then if we have a really big difference, then we will call that an ionic bond. So typically anything that's greater than 0.4 we would consider polar covalent, and also less than 1.7. So anything more than 1.7 difference in electronegativity would be considered to be an ionic bond. You can kind of visualize it like this. This shows the distribution of electrons. So in a pure or nonpolar covalent bond, you see how they are equally distributed around the different elements of the bond. And this would be somewhere between a 0 and a 0.4 difference in electronegativity. If we see a bigger difference, somewhere between 0.4, and this chart says 2, we'll also see 1.7, and we'll kind of use 1.7-ish as our cutoff, and you would be informed about what that cutoff would be. But this would be a polar covalent bond, so electrons are more around the atom on the left than they are on the atom on the right. And then ionic, anything greater than that 1.7, or like in this one it shows 2.0, this is where the electrons are transferred, and so there's such a big difference that the electron actually leaves one atom and goes to the other one. This is what I was talking about with kind of the different ranges of bond type. So we take a look at this triangle, and so we'd have metallic bonds, ionic bonds, and covalent bonds, and this is all based on differences in electronegativity. I like this one also because it shows metallic and then ionic, and then also divides the covalent into polar covalent and covalent. But this is just supposed to show you that there's really a range, and we define it very simply as covalent sharing, polar covalent, ionic. But if you look at it in real life, there's a little bit of a range of how ionic a bond is versus how covalent a bond is. Here's an example of the electronegativity values. You would obviously be provided with this anytime that you would be taking a test, or anytime that you would need it. And so these are the different electronegativity values. You can see that fluorine is 4.0, and then metals like francium all the way down at the bottom is 0.7. And so electronegativity in general increases as you go up and then to the right. There's maybe some differences kind of as we get into the transition metals. There are maybe some slight differences, but in general with the main group elements, meaning groups 1 and 2, and then our groups over here, that's what we'll see. Notice that the noble gases aren't included in this because they are not typically, I mean, we'll look at some exceptions with xenon, but they're not really bonding, so they don't really have those electronegativity values. All right, so let's do a little bit of practice. So electronegativity, so is the bond formed between each pair, ionic, polar covalent, or pure and nonpolar covalent. And so we'll use that 0.4 and under will be nonpolar covalent. Above 0.4 till about 1.7 will be polar covalent, and then above that 1.7 would be ionic. So go ahead and give it a try. So if we take a look at these, we have strontium, which is here, 1.0, fluorine, which is 4, so the difference is 3, so that would be ionic. We're going to treat all metals and nonmetals as ionic bonds. All right, so we have nitrogen and chlorine. So nitrogen is 3, chlorine is 3, so this would be a nonpolar covalent bond because they're sharing evenly. And then we have nitrogen, which is 3, oxygen, which is 3.5, so they would have a 0.5 difference, so they would be a polar covalent bond. Now, if we look at these, we can also talk about which side would be positive and negative. So if we're looking at nonpolar covalent, then there would be no positive and negative dipole moments or partial charges. With strontium and fluorine, fluorine is more electronegative, and so it will gain the electron, so it will be negative. With nitrogen and oxygen, oxygen is more electronegative, so it's going to hog the electrons more, so it would be partially negative compared to nitrogen that would be partially positive. So if we kind of practice that same idea, which atom is going to be negative relative to the other one? So hydrogen is 2.1, chlorine is 3, so the more electronegative atom will hog the electrons more and will be partially negative. You can go ahead and pause and try the other two. So if we look, carbon and oxygen, oxygen is more electronegative, so it will be negative. And then this is iodine and chlorine, so chlorine is more electronegative, and so it will be more negative compared to the iodine. Now that we've taken a look at electronegativity, let's take a look at polarity of bonds and molecules. And so the goal will be to determine if bonds are polar and nonpolar, and then to determine if molecules are polar or nonpolar. So polarity of bonds, we discussed how electronegativity determines the type of bonds. The difference in electronegativity leads to uneven sharing of electrons, and so will result in a polar bond. A polar bond is going to be when one atom has an unequal share of electrons, and so then it causes that to be partially negative. For molecules, molecules will be polar whenever there is an asymmetrical molecule, so the bonds don't cancel, or sometimes if there are lone pairs of electrons, that can lead to some polar molecules as well. So with molecules, the polarity of bonds can cancel, meaning it's kind of like a tug of war. So something like this, where you have a carbon in the middle and oxygen on the sides. The dipole moment is that oxygen would be hogging the electrons and so would be partially negative. But because it is a symmetrical molecule and it's linear, then you're going to find that those cancel out, and just because the bonds are polar, it doesn't mean that the molecule itself is polar. And so this would interact differently. So even though each of the atoms has a little bit of a partial charge, the molecule as a whole is not considered to be charged. If the bonds don't cancel out, then they produce a net dipole moment or a net partial charge. And so, and like I said, a molecule might also be polar if it has a lone pair of electrons. So we represent this dipole moment and the partial charge with this arrow. And so you can kind of see the positive and then it goes to negative. It's showing which way the electrons are going. And so we would use this little symbol here to represent partial positive and partial negative. Okay. when we're looking at shapes that we've discussed before, we have nonpolar would be something that's linear because those charges would cancel out, assuming that it's symmetrical and that the same element is on both sides of that central atom. We would also have nonpolar if it's trigonal planar because they're all in the same plane, and so the net force of these two going down would cancel out that force going up. The other nonpolar would be tetrahedral because, again, you're going to see a cancellation of each of those different poolings. Okay? The ones that we'll see polar will be trigonal pyramidal and then polar. So if the bonds are polar, then the molecule will also be polar. Now, if the bonds are nonpolar, then the molecule in general will also be nonpolar. There are a few exceptions, but in general that is the case. So why is it important? Because polar molecules will behave differently than nonpolar. Like oil and water don't mix. You've talked about this. You know this to be true. We talk about how like dissolves like. Like dissolves like because of these polar molecules versus nonpolar molecules and how they interact with one another. We talked also eating greasy food. It's difficult to wash off with just water. You need soap. This is because the soap has a nonpolar end and a polar end. So that nonpolar end interacts with the grease and the polar end interacts with the water in order to clean. And so that's, on a basic level, you've talked in biology about properties of water. Those are all as a result of the polarity of water and then therefore how it interacts with other molecules. We'll talk about those specific interactions next.